Hey everyone, welcome to another deep dive with me and Erik. This week we're looking at the Lunn exercise. This is sort of quite a straightforward exercise, but Erik and I just spent, well, actually about 40 minutes going through these solutions with Erik just trying to explain to me what is going on, because there is some really complex stuff coming up. So this is a video where I highly recommend getting yourself a nice cup of coffee or tea or some other caffeinated beverage of your choice, making sure you go back in time and have a good nap last night, and belt on your seatbelt, because we're going to be looking at some quite interesting code here. So I'm going to start off just by explaining the Lunn algorithm. If you've just solved the exercise, you'll know this, but I'll only take 30 seconds going through it. If you're watching this on YouTube and you've not solved it yet, then hopefully this will give you a quick overview. So I'll explain it firstly just using the introduction we have on Exercism. So firstly, we have the rules about validation. So, well, what is this first? It's a checksum algorithm. So it's an algorithm that's used to validate identification numbers. Things like credit card numbers, apparently Canadian social insurance numbers as well. So we start off by looking at the length of the string and seeing whether it is more than 2 characters long. If it's not valid. And you are allowed spaces in the input, but they are not counted towards the counting of the number of digits in here. And you're not allowed any other non-digit characters. So you're not allowed letters or symbols or anything like that. One thing that people get wrong is when you're working out the checksum, you start from the right, not the left. So we start from the right and we double every second digit from the right. So in this case, it's these digits here, as you can see, highlighted here, the ones that get doubled. If doubling any of those digits gives us a number greater than 9, then we subtract 9 from the product. So if you double the digit 6 and get 12, you take 9 away from that and you get 3. Then you add all of the remaining digits together, giving you a number. And if that number is evenly divisible by 10, then the number is valid. So that's our algorithm. So I'm going to start off just by talking about the Ruby one, because I think this is just a really clear example. And Erik's going to use his voice so much in explaining all of the more complicated ones in a minute that I thought this is a nice one to talk through. So this maps onto those instructions really clearly, as Ruby tends to do. So we take the input, we remove, this is substitute, a global substitution. So we remove all of the string characters, we replace them with, so all of the white space characters, we replace them with nothing. You could have also used delete here. And then we call this block using the tap method. And what tap does is it says, call a method on this, but ignore whatever comes out the other end and just continue. So we're calling tap, and this is effectively a guard clause. So we check against this regular expression. It's a slightly strange regular expression. Erik and I had to actually go and Google what these bits were to make sense. But this /a is the start of a string, the same as a caret that you normally use. And this /z at the end is the same as the $sign that you often see at the end of regular expressions. So it's just another way of writing these that we hadn't seen before. And then this checks that there are at least 2 digits, which you could also do by doing /d and then parentheses and 2 comma. But so this is a regular expression that just says, are there 2 digits, 2 or more digits? And if so, it's fine. Otherwise, we return false. Continuing on, we then get all of the characters, the chars, out of the string, and we reverse them because we're starting at the right and moving in. And then we go through and we map them. So we call a block here, a function on each of them. And we do so by also passing the index in. So we get each of the individual characters, which is the digit, and also the index as well. And if the index is odd, then we double the number. Otherwise, we just return the number as it was. And then we go through all of those numbers that we've got. And we say, well, if it's greater than 9, then we take 9 away from it. We subtract 9. Otherwise, we just keep the number. And at the end of it, we've got that final number. We sum the digits up. And then we check to see whether or not it is evenly divisible by 10. So this is basically these nice English instructions written out very clearly in some Ruby code. So we're going to dig in now to another relatively straightforward implementation of this. We're starting things off nice and easy. Erik, this is a C++ one. Do you want to talk us through what's going on here?
Yeah, so this C++ version uses a for loop, and it's using a for loop where the I, so the thing that you're looping over, using to loop, starts at the index of the last character. So that's the I is str.size -1, so that's the index of the last one. And within the loop, you at the end you do -i, and you keep on looping until you've reached a number less than 0, because that's the end. Of course, there's no index less than 0. So that's just a reverse loop. It's fairly standard. So line 8 to 11 are input validation. So first we're checking for if it's a space, then we can just skip over it. That's basically what we're doing. And then we're using the fact that in C++ and in many languages, you can compare characters. So you can check if a character is less than a character. So we're basically checking if it's a digit here. There are other ways to do that, but this is also a fairly common one. And if it's not a digit, we return false. So that's a short circuiting. If it is a digit, we are incrementing the digit count. And we had set the digit count to 0 at first. So that's keeping track of how many digits we've already processed. And that is what we're going to need to figure out whether or not we are at an even or an odd index. And we couldn't do that via just using I, because there are spaces there too. So that would just be, if there are spaces, it would be almost random. So you wouldn't know. So this is a way to make sure that you are actually counting the digits, not also counting spaces. Then there is a nice little trick here. So you see factor is 3 minus factor, and nothing is in the rules of the exercise to say something like 3. But the trick is that this is going from between 1 and 2. So if you go up a little bit, you can see that we start out with factor being 2. So before the loop is initialized. So the very first time that we get at line 13, we're doing 3 minus 2, which is obviously 1. So the next time we get there, we do 3 minus 1, which is 2. So you can see this is just flipping between 1 and 2. So this is a nice little trick to do this without having any conditional code. It's less obvious than the other version, but it does work well. Then on line 14 is where we're actually converting the digit, which is a character, so it's not yet numbered, to the digit value. So you do that via minus. So that's also a very convenient way, which many languages support. And then we multiplied it by the factor. And the factor is what we just mentioned, is either 1 or 2. So we get the doubling in place. Then there's a nice little if statement to see if we need to subtract 9. And we in the end, we add the digit to the sum. And then all the way down onto line 19, we're checking if we have found more than one digit and whether or not the end result of doing modulo 10 is 0, which means that it's even divisible by 10.
Nice.
Very imperative,
that was really
very clear,
nice,
I guess, to many people.
Exactly. Yeah. It feels it's doing the rules in like a slightly different order to the sort of way that we listed them out in the instructions, but it's very much still implementing the Lunn algorithm. So I think this is a very valid code.
And one of the reasons,
the header file as well.
Sorry. One of the reasons why it's also very good is that it does a single pass. So it doesn't do upfront validation, which you see many people using, where, for example, you would validate that all the characters are either spaces or digits, but this is just iterating through things once. So that's quite efficient, especially for larger numbers. I'm not sure how big Lunn numbers can get, but probably not that big.
Yeah, if you're passing lots of them, like you're trying to validate millions of social security numbers at once, this could be
definitely add up.
Important fix. Yeah, I mean, if you compare this again to the Ruby one, in each of these, we're basically creating new data structures. We're creating an array here, another array here, another array, another array. So this is dramatically inefficient compared to the C++ version here. Okay. Next up, we have a solution in Swift. This one also, Erik, is like relatively straightforward. But yeah, talk us through this one.
Yeah, it's a little bit like a mixture, sort of in between. So we start with a little bit of cleanup, and I like the verbosity of Swift here, replacing occurrences of with. That reads very well to me. Then you get a clean number, and then you get the guard keyword, which is like you're signifying that this is something that you really are you really want things to be true. Otherwise, you have to do something. So in this case, we're saying, hey, it has to be at least one digit, character in this case, because we haven't yet converted to digits. Otherwise, we return false. So very upfront validation.
And then we have, just to pause there, this guard clause is basically an if clause, but without the sort of the stuff that you execute if it's true. Basically, that's how it's being used here in Swift.
Yeah, that's true. Yeah, it's like an assert almost, but it's nicer. There are some other things that you can do with it, but it's a very common pattern to use a guard here. And then early return. So
yeah.
And then on we have two variables. We have the sum and odd, and odd will be the Boolean. So it's just true. They're both variables because they will mutate. And you can see that, for example, the clean number on the top is let, which means that it's immutable. As we won't be changing that. And then we can iterate over it. And this time we're using something like Ruby, so where we can do reverse iteration without having to do the whole negative indexing, etc. Then we have another guard. So converting the character to an integer. That could fail if there's like an A or a B, although that it could be asking maybe a Z or an F. And then once again, if it doesn't actually work out, then you return false, so another guard. And but if it's valid, we have a digit. And then the rules are, if it's an odd one, we just have the digit itself. We add the digit to the sum. And if it isn't odd, so it's even, then there are two ways in which you can do this. So this is basically combining the doubling and the doubling minus nines. So if it's less than 5, we will never get past the 9. So we don't need to subtract 9. We can just do the doubling. Otherwise, we do the doubling minus 9. And then finally, we do odd.toggle, which means true becomes false, false becomes true. And finally, sum.is multiple of 10 is, well, I find that incredibly pleasing because it's exactly what we want to check. So
that's really cool. Yeah, I think it's a nice example of showing off some nice features of Swift. That I like it.
I agree.
Okay, so next up we have Gleam. Gleam, the hot language of the moment. We've talked a lot about Gleam recently. It just released version 1. Again, congratulations to Louis and the team from that. If you're interested in Gleam, we've got a brilliant learning syllabus on Exercism for this. There was also a live interview I did, Q&A with Louis, the creator of Gleam, probably a year ago now. So do check those other videos out and do, Erik's done an introduction video as well. So we've got lots of Gleam content, and it's a really interesting, fun, hot trending language right now to dig into. But yeah, this is really nice and functional. Erik, talk us through what's going on here.
Yeah, this is moving on from the where Swift also had that guard bit where error handling was really explicit. Gleam has that, but in a functional way. So we can see that the core of this code is in lines 6 to 12, and it's a pipeline. So you start out with the string, and then we pipe that into 2 digits, which converts it to, digits. But then we don't pipe it into just a regular function, we pipe it into result.then. And result is a type that can have two types of values. It's in some cases it's left or right. It depends on the language. Sometimes it's okay and error. In this case, that is how Gleam has interpreted this. But this is the functional way of dealing with something that can fail. So either something is it's okay, or it errors. So the result type is either of these values. It can't be both. It can't be neither. It must be exactly one of them. And 2 digits is, well, it's parsing a string into digits. Obviously, that could fail. So if we look at the 2 digits function, we see that the input parameter is a string, but the result, the return type is a result of a list of integers or nil. So in this case, we chose nil because we don't really care about the actual error, because we don't need to propagate it or do anything with it. But that's the error case. If it's either nil, then it's an error, and otherwise it will be a list of integers. So the actual code itself, first we're stripping spaces, then we're converting the streams to, well, graphemes, read that as converting it to characters. And then we're trying to parse all these characters into integers. And that is list.try_map. So you pass that a function, in.parse. And what this will do is it will go over all the elements in the list, and it will call in.parse for each of those elements. But an additional thing that it will do is it will check the return value of in.parse, because in.parse could fail. So it will return a result type 2. So if the return value of in.parse is okay, then it will just continue with the next element until it is done. So if it is done and everything was okay, it will just return the actual values. But if at some point it finds that there was an error, it will stop and it will return the error case. So that's what we're doing here. So it's a functional way of sort of doing that for loop with the guard that we just saw in Swift, but in where you have the result type that encodes that bit of information for you.
And just to pause there a sec, I guess that this try map, does this need to return an error type that has the error value as nil as well, I guess, to match this type signature coming out?
Yeah. Otherwise, you need to map the
type
error
signature is the same as this.
Yeah.
Okay.
So you could have if in.parse would return another error type, then you would need to do an additional result. I don't know the exact function name, but there is a thing where you can transform the error type to the one that you want to.
Probably this.
Well, that is the default value that you get. It's not entirely the same, because if you unwrapping moves you out of the world of the results, but whereas you could you could want to stay in the world of results. But the thing about this result is once you are sort of moving to the world of results, with the world where things can and could go wrong, then you sort of stay in it for a long time. So you can see that we have result.then, and then we have result.map and result.unwrap. So all the code is here dealing with results. So result.map is basically the function that we pass in will only be called when the result value is actually okay, and then it will get that the bit of value that is in the okay value, and it will call the function with that. And then the result of that function must also be a result. So that's quite a bit of resultness, but that's basically a validation step, so that the length is greater than 1. You can see on line 22 to 25 that, well, we've seen this before, but Gleam doesn't have a regular if statement. So you do pattern matching on Booleans too. So very, very, Gleam is a very small, nice, neat little language where it doesn't have a lot of syntactic sugar, but you can get away with just having a pattern matching everywhere, basically. And it still works very well.
Nice.
And then, well, the rest is quite simple code. We have a checksum to validate. Well, these are just using built-in functions. Reversing index map is like the Ruby map.withIndex. So the digit value gets a digit and an index. And we do pattern matching on multiple values here. So on the digit and whether or not it's odd. So we're saying if it's a digit and it's odd, and the digit is less than 5, then we just do the doubling, which we saw before. If it's a digit and it is odd, so it won't have been less than 5, then we do doubling -9. Otherwise, we just do the digit.
Nice. That's really cool. Yeah, I really, every time I see Gleam, I like it as a language. It's, again, if you're not used to functional programming, it definitely takes like a bit of time to get your head around, and sort of, there's a lot more verbosity here than what we saw in, say, Ruby, which is doing its own weird Ruby thing. But yeah, it feels really clear. Like every function is so clean in what it does and how it reads, and so predictable in what comes out the other end, as you explained with the result types and things. Yeah, I think that's a really nice way. Even just something like this, using the pattern matching with the guard clause, which is similar to what we just saw in Swift, but it just feels so clear and clean here to see that. So,
although I'm not actually
really
matching
nice.
on the
Anything else you
digit
want to say
value
about?
at all. So
Yeah,
this is a mistake of mine. I think that was old code. So that we should just case on the is or thingy, but oh well, it's fine.
Yes, true. Cool. Okay. Let's move forward. So the next one we've got is R. We're looking at two that are sort of quite similar coming up, but yeah, we thought we'd start with R. We haven't seen much R yet so far in this series. So I guess the comments in this are really helpful just to sort of see what's going through, Erik. But you were sort of explaining to me before that this area is where the sort of unique stuff is. But yeah, do you want to start at the top and just talk us through what we're seeing here?
Yeah, so the lines 5 to 8 is basically, line 5 is input cleanup. So we replace spaces with empty strings, so removing spaces basically. Then you do split to convert the string to a vector, so the individual characters. And then on the next couple of lines, we just do validation, see whether or not the length is less than 2, or there is a non-digit value. If so, we return false. So that's all input validation stuff. Then we get to the more interesting bits. So we're doing as numeric, but we apply that to a vector. So these are multiple values. So these are all the digits. And there are at least 2 because we just checked that. But we don't need to have a for loop or anything. That's all built into R, that you can apply functions to the entirety of a vector. So this will call as.numeric on every single value in the vector, and you get back the numbers. So that's an easy way without having to loop. You can see then on line 14, we are reversing because, of course, we want to start from the right. And then we get to the bit where vectorized operations become really cool, where you can use between the brackets is indexing. Normally you just, in many languages, you can do a range. Usually you can just do an index, like a single number, but you can, in R, you can pass in a vector of indexes. So we're creating a sequence that starts at 2. At most, it is length num vector, so that's the uppermost value, and we increment by 2. So this is 2, 4, 6, 8. So these are all the even indexes, which isn't surprising because that's what we want to do. So we're basically saying all the values at the even indexes are assigned. Okay, so what are they assigned to? Well, the same values, but times 2. So you can apply times 2 to a vector, and it will apply times 2 to every single element in that vector. So what this will do, it will take all the elements that are at the even indexes, multiply them by 2, and then basically override them. So
nice.
And that is what's being done here, and it's incredibly powerful. And once you get used to that, you sort of start missing it in other languages. At least that's what I felt.
Yeah.
But there are more languages.
And then this just carries on through.
Yeah.
With a little if else.
Yeah.
Even that's quite a nice little bit of syntax as well, isn't it? Just being able to call an if else function with the 3 things. That's
so basically
you see often.
Yeah. So this also applies to every element in the vector. So for all the elements for all the elements in the vector where they're greater than 9, then you subtract 9. Otherwise, we don't do nothing. But you don't see any looping here, but that's all implicit.
No. Yeah, exactly.
And then in the end, we just do sum.
And then finally, just
we've seen that before.
Yeah.
But the beauty lies in the
That's very cool to
vectorized
see.
operations.
Yeah, and this again, we've talked about this in the past, but when you have vectors, this is where you can start to make use of parallel computation, GPUs, all of these things. This is what powers the whole AI revolution that we're seeing at the moment. Maybe not at just 16 numbers in a credit card validation, but if you called this code on a vector of lots and lots of credit cards and you expanded it in that direction as well, this could become very, very, very efficient and effective. Very cool. Okay, so now we have Pharo. Pharo, very unlike what we've just seen in some ways, but talk us through this, Erik.
Where do we start? Probably that the fact that the syntax is quite unlike what we've seen before. Pharo is a very unique language, a very powerful language, and if you just remember one thing about Pharo is that it's a very pure object-oriented language, but it's not your typical C# Java object-oriented language. It's actually a small talk language, which means that you're sending messages. Ruby took a lot of inspiration from that, I think, too. Other languages have too. So what we're doing is you have objects and you send messages to objects. You're not calling methods, you're sending messages. You might think that's like semantics, but it's not entirely so. But in this case, for example, on line 16 to 19, that is validation. So we're saying the head, the caret at the beginning means return the value after this. Otherwise, if you don't do that, the object itself will return. That's this message is being called on. So we're doing all satisfy, which is all. It has to something, you get a Boolean value back, and all of them have to be true. Otherwise, it will fail. So the bits between the square brackets are blocks that are executed. So like anonymous functions. And colon each is the variable name within the function. So we're saying each is digit. So is digit is just a message that you can send to a character, and then you do another block, and it must be a block because it's you want it to only be executed whether or not it's the first one is true. So otherwise it would have already been executed. It's very funny to see how Booleans are implemented in Pharo. If you ever want to have like a little Pharo moment, look up how Booleans are implemented. It's really cool. But it's basically just saying everything has to be either a digit or a separator. So is separator is also built in. That's just spaces, basically. I think it might also be tabs or whatever, but white space, I guess. So the really most of it is fairly similar to what we've seen before. So you have the digit only string on line 23 if the size is greater than 1, but it is false, so it's not greater than 1. Then we just return false from the function. So that's like a short circuiting, an early return. Otherwise, we do format to Lunn, and then we have the digit only string. You convert that to the number, the digit sum. So we don't need to go into everything. That reads very well. But there's one little trick that I want to highlight in this bit of implementation, which is on line 31. And that's the Lunn digit for a digit character. So this is doing the doubling. So we see a digit car, digit value. So that's just converting a character value to is actually a digit. So the 9 character to 9, etc. So doubling it. But then you do digit sum. So what is that? There is no -9 or whatever. That's not in this code. So let's talk this through. What if the number is, the digit is 1? Then we double. Digit sum means converting a number to all of its digits. So for 1, there's just one digit, 1. So the sum of 1 is 1. This becomes interesting when the number is actually results in something that's greater than 10 or greater or equal to 10. So suppose the digit is 6. We multiply it by 2 and we get 12. So 12 has 2 digits, 1 and 2. So normally the rules are, if it's greater than 9, you subtract 9 and you get 3 in this case. So, but if you do 12, you have 1 and 2 as digits. If you sum them, you get 1 plus 2, which is also 3. And amazingly, this works out for all the other numbers too. So 7 times 2 is 14, minus 9 is 5. 14 is the digit 1 and 4, which is also 5. So this is a neat little trick where you don't have to do the minus 9. And I found that a very clever implementation.
I remember being a kid and you can memorize these like magic trick sort of number things where you get everyone in the room to like come up with their own number, and then you get through, and at the end basically everyone's number has got to the same, and you can sort of guarantee that people get to the same number, so you can tell them what their end number was. And it seems like this real magic trick because somebody can choose any number to start with, but you can end up getting them to the same number. And I remember this little trick, now you've said it and now you've talked it through, being one of those things where you can use these like little patterns where doubling and taking away 9 is the same as adding the digits and things. So I think, I came across that as a kid and I've not thought about it for a very, very long time since. That's really cool. Do you have a look at this solution in more depth? It is really interesting. That's a cool little trick that could be applied to any of these solutions. And there's another way here that sort of does this in a slightly different way as well, Erik, and attacking the same element from a different problem, and that's Glenn's solution in Tickle. And I guess this is the interesting bit on line 10. But do you want to just quickly talk us through the whole thing? I guess this top bit again is just validation, is it?
Validation, and that's basically it. And so we get reg sub, so that's regular expression substitution, so spaces are removed, then checking if it's the length, etc., and whether or not they're all digits, which again is using a regular expression. So that's all fine. Then we get to double, which is a variable, which initially is false because we're at an odd index. And there's a for loop. So it's a reverse for loop, L reverse, splitting of the digits on an empty string basically means we get all the individual characters in the string. So the digit. But the thing is, if double on line 9, then what we do on line 10 is interesting. So there's no digit sum. There is no multiplication by 2 with minus 9 or whatever. So what's happening here? So what this solution does is to use the fact that the digit could also be used as an index into in an array. So that thing between the curly braces, if you have the digit 0, so the leftmost one at the index 0, if you multiply 0 by 2, it's of course 0. Then the digit 1 on which will be the element at index 1 is 2. So 1 times 2 is 2. Well, obviously 2, 4, 6, 8, it's all fine. Then we get to 5. So index 5 should end up with 5 doubled is 10, minus 9 is 1. And that's what's in this array. So basically, this does away with that whole doubling shenanigans and just gives you the actual the value that you end up with just by using the fact that the digit could also be an index into an array of size 10.
It's basically a lookup table, isn't it?
It is, yeah. It's very
in
clever.
effect, you've pre-calculated the values.
Yeah.
Nice. And then the rest is just pretty straightforward. We add the digit to the sum, I presume that is.
Yeah.
Reverse the doubling, and then at the end we check whether it's divisible by 10 or not.
Yep. So clever solution.
Nice. That's really clever solution. It arcs back a little bit to the NIM ones we've been looking at in some of the other videos where we sort of pre-calculate everything. But nice to see that here. Okay, cool. Nice work, Glenn. Raku. We had Raku in the video that we released yesterday, which is Perl 6. I explained in that video. If you're not familiar with Raku, it forked from Perl. So very, condensed solution, 7 lines as we expect. And there's a few bits going on here, Erik. Do you want to start? I guess we start on line 7, don't we? You were saying before.
Yeah. So we see 2 is Lunn valid definitions, and multi means it's a multi-method. I think that's how Raku calls it, which means that there are multiple implementations with the same name. And then the runtime can decide which one to call first. And in this case, at least how I understood it, that what you're now highlighting is called first, which is the validation rule. So Raku and Perl are very often used with regular expressions. They're absolutely great at that. And this is basically saying validate that if there is a not number or a space separator, then already return false, because then the input is not valid. So it's all like a guard, but it is at the function level, which is also more like maybe an Elixir or an Erlang. And multi-methods are in other languages too, but they're quite a neat feature. So just see that as validation happening before we then get to the actual input being processed. So that's on the other. So the bulk of the actual implementation is, of course, in the other method. So you have input dot comb, was it right? I keep on saying coom, but it was comb, of course. So that's converting the string to the individual characters, and then getting the numbers. So there could still be spaces in them. So this is just getting the numbers. And then if you see on the beginning of line time, it says with. So with means that you're executing the block in the context of what gets returned. So then you get return false if .elms is less than 2. So the end result of all this filtering, you get an array. So you do .elms. So this is, of course, validation again. But then we do a couple of very succinct calls on line 4, starting out with .reverse. Well, that's the simple one. And then we get to something that's quite neat. So we recognize the star in the middle, which is multiplication. And the 1 and the 2, you probably also recognize, where it's doubling. So the way that this works, it is like zipping them together. So where you do a multiplication via 1 for the first element, via 2 for the second, then 1, then 2, then 1, then 2. So this whole combination of multiplying by that either 1 or 2 values, that's all being done in those, I don't know, what's it like, 10 characters or something like that. So it's incredibly succinct, but that's what's being done there. And Raku will handle all of that for you. So after that, we've done the doubling. So then we need to still do either the -9. And interestingly enough, I found that they are using the same trick that the Pharo people were using. So you have, we're mapping all the values. So within the map, we are in the context of a single number. We're saying comb again. So we're converting the number to individual digits, and then we're doing the sum. So it's the same digit sum trick that was in the Pharo Smalltalk implementation. And then in the end, we sum all the values and check on or not. We don't have equals 0 because that's truthy and falsy. So, but that's it. So it's a mixed mash of the R vectorized operation thingy and a bit of Pharo here. So it has a lot of cool things going on for it.
Nice. I think the things that jump out to me, this with is really cool. The fact that you can just call then methods, on this ethereal object that's been passed in, and then this bizarre pattern matching sort of thing is very unusual and cool. So yeah, really nice solution. Good find, Erik.
This was
okay, and then we're going to move on to
the one solution that I didn't find myself.
Oh, really? Nice. Okay.
It was.
So we're going to move on to the final one, which is the one that Erik, after about 15 minutes, was like, "Oh, I definitely understood this yesterday. Why do I not understand it now?" When we were looking through this, just say. It is complicated. This is the first solution we're showing from our new SQLite track that we launched last week. I'm not sure our SQLite track is going to get you good at using SQL for anything particularly useful in life, but it's definitely going to get you good at just the concept and the language of SQL, because solving all of Exercism's exercises using SQL is a really interesting challenge. So Yeah, Erik, we're going to take this slowly. I'm going to interrupt you lots every time I
Mhm.
don't understand what you're saying, and we're going to work our way through this. But yeah, this is definitely a good time to make sure your tea or your coffee is topped up. I've just run out of tea, which is not a good thing for me. But yeah, let's start at the top. Let's just take one block at a time, Erik. So
Yeah.
yeah, what's this with clause doing?
So SQLite supports recursive queries. So
Mhm.
with recursive means that there's recursion going on. If you don't know about recursion, we have done previous videos on that. But this is for us a way to generate a sequence. So we're first generating one. So that's to select one.
Mhm.
Then we're union all. So means combining the result of that with calling
Mhm.
ourselves again. So we say select n plus
Mhm.
1 from indices. So then you get 2. And then the next time it will be a recursive call again. So you do 2 plus 1, etc., etc. So basically, you can just see this as generating the range of numbers from 1 up until n, or that's the least. So
Okay.
yeah,
And what's
with
the
a
limit?
limit.
50?
I think that's sort of arbitrary almost. Maybe it's just
Okay.
for safekeeping. I'm not definitely not a SQLite expert, so feel free to correct me if anything
Okay.
I say is completely wrong. I started with this myself, so
so so we've effectively got like a recursive function here called indices that we can then call later on to get a list of all of the numbers
yeah,
up to n.
yeah,
Okay. And then we've got this next. And I mean, they're not really function. They're not functions, aren't they? Clauses, I should say. Clauses with called valids.
hmm
Uh, so what's this doing, Erik?
yeah. So it's invalid is like a temporary table, and what we
Mm-hmm.
insert there is something that's very that you see a lot when you do the SQLite track is where you do a little bit of transformation on your input data to make it easier to work with. So what we're doing
Mm-hmm.
here, so it says on line 10 from Lunn. Lunn is the table that
Mm-hmm.
you are working with. So that's at the top
Mm-hmm.
indeed. So it has a text field called value. But that's like
Mm-hmm.
the unsanitized version. And we've seen in every single solution that we've seen that there's a bit of sanitation going on. So
Mm-hmm.
basically what we're doing here is we still return value, but we
Mm-hmm.
also do a second column where it's the replace
Mm-hmm.
value, where all the spaces are replaced with nothing. So they are removed.
Mm-hmm.
And then there's a little regex validation again. So
Mm-hmm.
the value must match at the start. So the digits or spaces. So they can only be digits
Mm-hmm.
and spaces. Um,
Mm-hmm.
and I think the second thing is I wasn't entirely sure. So it's removing all the spaces,
Mm-hmm.
and that can't be 0. I assume that's because it's an empty. It's like the string length, but I'm not entirely sure. What does
That's
it do?
strange.
What does it do?
I feel like. Well, I presume it's checking literally whether the string is the string of 0 at the end of it.
Well,
Um,
but why?
maybe they've slightly misinterpreted the rules, and the test cases in the SQLite track let you get away with that guard
Okay,
instead of
yeah.
the
Maybe we
actual
should
guard,
just skip over
because this
that.
isn't checking this. Yeah, this isn't checking whether there's more than one digit. It's
No,
checking whether there's more than one digit.
yeah,
Anyway, but you could easily change this little bit of code to
yeah,
match the correct requirements.
yeah, absolutely.
So we've got a temporary table called valids now, with
hmm
2 columns of values and numbers, which are effectively the same. It's
but
just the
still
one
a
has had
string.
all the spaces stripped,
Yeah,
but still a string,
yeah,
crucially. Yeah, even though it's called num.
yeah.
Uh, and so
And
then we're going to go through and uh,
yeah,
get some more data, build another. Yeah,
we'll take this slow. So on line
yeah.
16, we're getting the values from valids and indices, so from both tables.
Mm-hmm.
And on line 17, that's our recursive thingy where we're saying n must be less than
Mm-hmm.
or equal to the length of the number. So
Mm-hmm.
that's limiting our recursion. we're doing group by value for regions that we will get back to. So now we come at the meat of it, which is on line 15. And for this, we have to start slow here. So the indices are, of course, the indexes. So 1, 2, etc. We need to go from right to left. So the first thing that we're going to look at is the thing where it's between parentheses length num minus n. So that is the index of the, so that's the length minus the index. So that will be 0 for the rightmost one, or it will be 1, and then there will be etc. etc. So, and then you do modulo 2, which gives you, for the rightmost index, it gives you 0, and then a 1, and then a 0, etc. So this is basically working from right to left. So that's the easy-ish part.
Yeah, let me just interject here. So if number, for example, is the 16-digit number that we're working on in the first place, and then we're going through and we are looking at each of the valid. So where is n coming from here?
From the indexes.
It's not clear to me.
It's from the recursive table.
From the indexes. Okay, so we're looping through. Yeah. Why is it called n? Am I being stupid here?
I think that's the name at the top of the recursive. So at the method name there.
Right. Okay. So I don't understand how it works, but I'll go with it. I'll believe it.
Well, let's just assume it is, because that makes it a lot easier.
Let's just assume it is. So it's pairing up. It's pairing up the. Okay. So.
Well, valid only has a single.
So we're going to go through each of the indexes. Each of the indexes we've got.
Yeah.
Up to, we're grouping through here up until the length of the number. So we're starting with, say, length of the number is 16.
Yeah.
And our index here is it 1 or is it 16 the first time?
I don't know what is the first, but it doesn't matter. So there's no ordering.
Okay.
We're just doing addition. So it doesn't even matter whether or not it's the first or the last.
Okay. That's a good point.
Yeah.
Okay. So so let's say I got you, because we're only caring about odd and even here.
Yeah.
But do we not need to reverse the string somewhere?
Well, that's what we're doing here. But we don't care whether or not we start out with the first index or the last one. So the last index.
I see what you're saying. Yeah.
The last index will be 16. So then you get length of number 16 minus 16 is 0. Modulo 2 is 0.
Okay, got you.
Yeah.
Okay. So let's start in our minds by looking at number 16. So the length is 16. So this is coming out as 0.
Yeah.
We divide that by 2 and get 0.
Modulo 2, yeah.
But if we were looking at number 15, this would be 16, this would be 15. We would get 1 back.
Yeah.
Divided by 2, or modulo 2 rather, is giving us 1 back out of that. So that's our odd and even pivot.
Absolutely.
It's giving us either 0 or 1. 0 for even numbers, 1 for odd numbers.
Absolutely. Yeah. Okay.
And then we're timesing it by this magic 1.2 that we'll come to in a minute.
Yeah, exactly. So let's do
and then adding 1 to it.
Yeah, the rightmost bit first, because that's simple. That's probably what people can easily grok. Yeah. So substr num, n, 1. So on the very right, that's just getting the relevant, the character at index n. So we just get 1. So we start at index n and just get 1 character. So that's simple. So this is the digit. Okay. So read that as digit at position n. And then we come to the magical number, I guess. So remember that the thing on the left is either 0 or 1. So it's 0 for digits that we don't double, and it's 1 for digits that we do double. So in the case of 0, 0 times 1.2 is 0. You guessed it. Because 0 times something is always 0. If it's 1 for the double case, you get 1 times 1.2 is, unsurprisingly, 1.2. Okay, so we got that covered. It's 1.2 for double cases. It's 0 for non-doubling cases. Then we add 1. So, okay, so what do we get? We either get 1 plus 0, or we get 2.2 for the ones that we do double. So we're working with either 1, which is where we don't double. That makes sense. We've seen that before. Multiplying by 1 is not doubling. But why do we double by 2.2? We're multiplied by 2.2. That's not exact doubling. It's like almost random, but it's not. So this is where we have to get some actual examples in. So let's start with where the digit is. So we're only going to talk about things that are being doubled here. We're forgetting everything that isn't doubled because that's just multiplying by 1. That's easy. It's only in the case of doubling a digit that we get to work with the magical 2.2 number. So suppose the number is 1. So in the regular version, it's doubling 1 becomes 2. So that's it. In this version, doubling, we do 1 times 2.2. So we get, 2.2. But you see on the left, there's a floor, which means rounding down to the next nearest integer. So 2.2 floored is 2. So that holds. Okay, let's do 4. Doubling 4 gives us 8, but 4 times 2.2, that is 8.8. So we get another number. So 8.8 floored. Wait, why? Did I get my math right, by the way? Yeah, 8.8. Yes. Okay, so just double check it. 8.8 floored is still 8. So we're still golden. So when does this sort of become magical? Well, you probably guessed it. In the version where there is something happening with doubling, getting over that 9 limit. So if we have the digit 5, normally we would double it, we get 10, we do minus 9 because it's greater than 9, and we end up with the number 1. So what happens in this SQLite version? So you do 5 times 2,2, which leaves us with 11. So 11 isn't the same as 1. So floor of 11 is still 11. Previously we did 1, now we do 11. Isn't that breaking everything? Well, it turns out it isn't, because you have to consider the fact that in the end, we are doing things modulo 10. And 1 and 11 modulo 10 are the same thing. So it doesn't matter that we have an additional 10. And if you're not convinced, let's just do one other example. So let's double the digit 7. So normally we do 7 times 2 is 14. Minus 9 is 5. Okay, that's fine. Now we do 7 times 2,2 is 15.4. We floor that, becomes 15. And 15 modulo 10 is the same as 5 modulo 10. So this nifty little trick was quite hard for me to figure out at first. But in the end, it's exactly the same as just doing the doubling minus the 9. And the floor, of course, has to be used. That's a little trick. But I found this incredibly clever, albeit entirely unobvious to, at least to me. Maybe that's me, but
yeah. So what do we then get at the end of that? So we're getting this sums back that's got 2 columns. It's got the initial value that's coming in, and we're also getting this digit sum value. We're grouping these by the value, which just will give us, I guess, 2 columns. No, it will give us one column with the valid in, and then all of the indices, all of the individual.
You need the grouping to work with the sums.
Yeah.
Those work together.
Yeah. And so then we're ending up with updating the results table, which is how this works in as the equal track. Regular expressioning
Validation
this.
again.
Why are we doing
there's duplication here. I'm not entirely sure why they do that, but probably because they don't merge.
I guess because okay, it doesn't matter.
Doesn't matter.
We've got this same guard.
Yeah.
But then this is where we're then doing the selection from here and then modulo in those two.
Yeah.
Magic.
Yeah.
Yeah, okay. And this group by is working on this sum. I haven't
Yeah.
clocked the sum there. Okay, so that's working as a
Because you
pair.
do that whole thingy per digit. So you need to group them all together
Yeah.
and then sum them.
Got you. So the grouping function here is the
Yeah.
sum function.
Yeah.
Okay, well, you might have been watching that and thought, this is really easy. I don't know what these two are getting on about. Why is this so complex? Or you
Let us
might be
know in the
feeling
comments.
totally lost. I suspect there's a whole spectrum. Please let us know whether we're just a bit slow and getting old and this is really obvious to you, or if this is way too complex and we need to do it at half the speed next time. Leave us a comment and tell us. But definitely, if you look at this and also you're thinking, why is this duplication here? What's this? Feel free to go and try the SQLite track and see if you can solve this. We need to factor in SQLite to be the featured language at some point during this 48 and 24 as well, Erik, because we don't have that at the moment.
Yeah.
So we need to think about where we're going to force SQLite on people this year. But probably not this one, is my initial instinct. Okay, great. Thank you for talking us through that, Erik. I hope if you watched that was a fun tour. We started off, I think, really clean and easy in Ruby and have gone on a bit of a stretch. We've looked at a few different sort of hacky, cheaty techniques to do things, which I think has been fun. It's a really interesting exercise. Thanks so much if you suggested solutions. If you've got great solutions to these exercises, by the way, please do let us know on the forums. We put posts up for probably about 4 weeks in advance to let people post their solutions on there. If you've got a really exciting solution to an upcoming exercise, just jump on the forum, check what those exercises are and let us know. But yeah, we always love it when people link to their solutions in YouTube comments as well. So please feel free to do that. Otherwise, I hope you have a great rest of your day. Thank you so much for watching. Please give this a thumbs up and I'll see you in the next video. Bye for now.